and Google and so far. But I never did, because I changed my mind after I got my master's degree in electrical engineering and computer science. And I found computers actually boring. And when I was attracted by the mystery and for neuroscience, and eventually pursued my career in neuroscience, we call brain research in many parts of the world. And I have been doing that for last 25 years or so, and having a lot of fun. So one of the messages that I want to deliver to students who are engineers here, that you can study brain if you just get interested. You do not have to be a biologist to begin with. You can be a good engineer, physicist, mathematician, and study brain from different perspectives. And that you can see from some of the work we've been doing. So I'll talk about mostly the work I've been done in John Hopkins in my laboratory. And at the end, I want to share with you a new adventure I've been taking in the last 2-3 years in Tsinghua University in Beijing, where I've been leading a new research institute to study brain and artificial intelligence. So I'll share with you some of that at the end of the talk. Now, the outline of my talk today are those 4 points. First, I want to talk about the neural transformation of stimulus selectivity from outer nerve to cortex. And Dr. Saragampa this morning already started this discussion. And then you talk about 2 specific examples of cortical processing of time-varying signals. We call it temporal to rate transformation, and harmonic processing of the cortex, which is related to music and speech processing. And finally, I'll talk about the auditory-vocal interaction. This is concerning speech processing. Now, the take-home message are the following. And if you forget everything else I talk about today, here perhaps 2 useful piece of message for students to take home. Now, when we talk about computational principle of a central nervous system, here are 2 points I always use when I give a lecture to students. First, central nervous system neurons can extract, or what we call compute, stimulus information not explicitly encoded by sensory receptors. But this is very important. Second is that the central nervous system transforms isomorphic or faithful representation of sensory stimuli established in the peripheral to non-isomorphic and perceptual representations in the cortex. Now, these 2 points will become more clear as we go through examples. And this faithful representation in the peripheral, Dr. Saragampa this morning gave you a very nice demonstration what is happening in outer nerve and the cochlear nuclei. Now, I've spent most of my career studying the auditory system. That is the system that governs our hearing. So many of you here don't study auditory system. You would naturally wonder, why do we study auditory system? Here are some reasons. Auditory system is crucial for the function for speech and language. This is very obvious. This is actually what I got myself and many engineers into the neuroscience, because I become interested in neuroscience mostly because of speech. Almost all electrical engineers are interested in speech. I eventually become interested in how the brain processes speech instead of how computer processes speech. So this is a huge category of auditory system function. Second category is just equally interesting, perhaps even more interesting, is how the auditory system processes music, sing, and poetry. This have a profound interest to the society, but it hasn't got much attention in neuroscience literature until recently. And I will share with you some of the work we've been doing along this line. Finally, there are a number of dysfunctions, diseases such as deafness, tinnitus, stuttering, schizophrenia, autism. All of them have something to do with the auditory system. So if we understand how the brain processes sound, and we can gain tremendous insight into such issues. Now, to understand the auditory system, it's a nice way to start for the engineer. It's a speech. There's a spectrogram I think most of you are quite familiar with. English sentence plot in the 3-dimensional space with time, frequency, and intensity. Okay, this is you see all the time if you study speech processing. But speech is complicated. In addition to the meaning that is writing in the sentence here, it has other information, for example, pitch, which we'll touch upon later on. That gives the information of intention, emotion, all of that. That's what we call paralinguistic cues. Now, what about music? If you plot music in this same three-dimensional space, it's like this. Okay. Again, frequency, time, intensity. Now, if it's just a pure tone, it will be like this one line here. So that's you can see music has a lot of what I call the amplitude modulation and spectral modulation that is very much dynamic, similar to speech. Okay. These are the two classes of signals that is most important to our hearing, to us, and to some extent to animals as well. Okay. So where is the brain in the cortex? Audio information is processed. It's here. It's called here, audio cortex. Now, by now you've heard lectures about visual system, and then the visual system V1, area 17 is here, and then you have other parts of visual system going this way and that way. Here is some of the sensory system responsible for touch, and the motor system, motor cortex responsible for action. Front of the head here, back is here, up and down. Okay, this is classic medical school textbook brain structure if you've never seen that. But the human brain we have now is unique, but it's also evolved from other animals. So here is the human brain in comparison to older world monkeys. Those are monkeys like the one around here in India, and the newer monkeys. These are monkeys in South America, which we'll talk about here. Okay. So if you look at their brain structure, they're largely similar, with the human having the most expanded frontal cortex in front of our head, forehead, less so in other animals. But the parts of the brain that process sound, we call it audio cortex, is largely preserved in either humans, old world monkeys, and the new world monkeys. And here's a picture of this new world monkey. It's called marmoset, and you have heard several times by now. Okay. So one way to understand the brain is to understand how the brain evolved, because it's our capacity to look into individual cells in human brain is quite limited, both technically and ethically. So much of neuroscience has been done in animal models, some of them in non-human primates or monkey models, that gain the insight into the human brain. That's the way biology has been working. Now, audio system, central pathway, you have seen this earlier in Dr. Zhou's talk and Dr. Xiaoqin Wang's talk. But I will show you one more time. That is the auditory pathway, and talk about what is unique about auditory system. So here's the ear. Within the ear, there's a cochlear you heard this morning. From there, signals goes into the next stage called cochlear nuclei. You also hear this morning. Now, sound in the air travels as basically waves. And as Dr. Xiaoqin explained to you this morning, is converted into action potential here. It travels to several stages. Marked here, eventually reach the first stage of cortex we call the primary outer cortex. The number within the parenthesis indicates synapses. This is a biological term. Engineer, you can consider this as a processor. So this means process once, twice, three times. So by the time signal, sound we hear, travel all the way into the cortex, it has been processed 5 to 7 times. So this is a serial computer with many parallel processes along the way. The sound process Dr. Zhou talked about this morning takes place somewhere here, because there's a left ear, right ear, and the sound from both ears combined here. That's what we call a binaural process, which I will not touch. So what is unique about audio system? So by now you heard some lectures about the visual system. You should have some idea about visual systems. The difference between audio system and visual system first is that the auditory system has a longer subcortical pathways. Now, the equivalent of a cochlear is a retina. And if you remember, from the retina to the cortex of visual system is much shorter. The audio system has a longer one. And this is a useful comparison because I also find for students to learn different systems, it's very useful to contrast them. So I'm trying to contrast the auditory system and the visual system. There's longer subcortical pathways. You'll see that in the next slides in the back-to-back comparison. Secondly, how the signal are processed in the visual auditory system are very different. In auditory system, we call sound coming here is spectrally overlapping and the time varying. So what it means is that cochlear, as Vassin explained this morning, cochlear acts as a Fourier transform. It only have one frequency access. Whereas when we hear sound from everyone in the audience or from the background, they're all on top of each other. In engineering, we call it spectral overlapping. This is a killer for computer processing speech when we have signals on top of each other. Signaling, when the signal into our ear sound is time varying. Acoustic signal is like water running in a stream. It's never still. It's always running. In vision, you have still pictures. Now, of course, you have movies. But audio system, time is an essential axis. That becomes tricky when we build models. Okay. Third, our ear is open. We don't have equivalent of eye lips. So sound enters the ear from anywhere at any time, 24/7, whether we're awake or asleep. We hear sounds all the time and from the front or back, anywhere. Okay. This is unlike any other system. We have an essentially open microphone in our brain that all day long. Last but not least, whenever we hear sound when we speak, we hear ourselves too. So this is the hearing and speaking process together. It's a sensory motor processing, just like the one I'm doing now. I'll give you an example. This is not trivial to push your microphone very close to your speaker. So those are the properties of an auditory system. That's a unique comparison to visual and somatosensory system. So when we talk about auditory cortex in the brain, it's just not the one bob. The auditory cortex I show here on this plot here, number 7 here, is the beginning stage we call the primary auditory cortex, which is right here. From here, signal go to other parts of them. In monkey brain, we have 3 layers of structure. This we call a core. The core auditory cortex, it has A1, R, RT, 3 regions. You can consider 3 massive parallel computers. And then we have second tier called a belt. That's around here. Belt also has several regions. Then we have a third tier called a parabelt. So in V1, you have V1, V2, V4, MT, IT. This is an analogy to that. After that, after the 3 tiers of processing, signals go into frontal cortex, eventually go to motor cortex. So those are 3 levels of processing in monkey auditory cortex, similar to other mammals. So from there, signal travel from where auditory cortex is. We call STG, supratemporal gyrus, to front to the frontal cortex or to back to frontal cortex. This is so-called rostral and caudal pathways. Now, you remember in visual cortex, also from V1, signal travel to this way or this way, even to actually merge in frontal cortex. So in summary of a grand picture of auditory information, sound coming from ear all the way to primary auditory cortex. From there, go to secondary auditory cortex and the third tier of auditory cortex, and then travel to the frontal cortex. And some people suggest that this pathway is for where information, that is the location, and this pathway is for what information is of meaning. But that's a very simplified view. Okay, so that is about schematic of information flow. Now, the next interesting question is, what is gate process from all the stage? Okay, and any engineering system diagram will ask us, why do you want to process? We look at computer, we know exactly what a gate process from microphone all the way to CPU. Okay, so here is a schematic showing conceptually what the auditory system is supposed to process. Sound coming here, as we say, is a wave. Okay, the first stage in auditory peripheral or brainstem, this is what Dr. Vassan, Sadagampa talked about this morning. We call this isomorphic representation. That is, what's in the sound has to be captured by the initial auditory system. It's just like you put your hand in the Xerox machine, you have to take a picture of this. Then what's got interesting and challenging is the next stage. From isomorphic representation, somewhere in the brain, likely in the middle brain and the primary auditory cortex, is transferred into non-isomorphic representation. Representation of outside world, but is no longer faithful. I will give you an example of this. Then it got further transformed, perhaps in a non-primary auditory cortex, belt and parabelt, or even frontal cortex, into what we call perceptual representation. This is what is directly linked to what we hear. Okay, we hear a word, we hear music. Eventually, is this representation. So the challenge for us as a neuroscientists or engineers alike is to understand this series of transformation, because eventually this is what explains what we hear, what we understand, or eventually what we call intelligence is here. This is a pathway. I'll give you 2 examples. One illustrates this, one illustrates that. Now, auditory system has lagged behind the visual system in terms of studies for for about 2-3 decades. But in fact, people who actually made huge discovery in the visual system, these two names, all of you should be quite familiar now by now, given the previous lecture in this workshop. David Hubel and Thorsten Wiesel, who made the discovery for them to get a Nobel Prize in medicine for their work in visual cortex. David Hubel, before he began his work on visual cortex, in 1959, before most people, I'm sure before all the students are born in this room are born, he actually, the first work he did, 1959, is to study the auditory cortex. So he wanted to study pre-electrode in cat's auditory cortex, try to drive a neuron. But published papers say essentially he cannot drive a neuron. Okay. So here are the spikes that you've seen many times. Here's the sound he played. He said this unit, he referred to neuron, almost never responded to click tones, noise from nearby speaker. He cannot drive them. Okay. That's what happened. Cannot drive a neuron does not respond to the sound he played. Then out of desperation, he tried things that is not quite rigorous. So this unit he eventually found responded briskly to voice squeaks emitted by squeezing a toy rubber mouse, scratching fingernail on the table nearby, hissing, tapping the table. All of things that are uncontrolled. So eventually he concluded finally it has proved impossible to discover the stimuli adequate for driving many of our cortical units. In fact, we cannot readily explain. And he will move on to visual cortex. The rest is history, as you know. Okay. So why can't he drive auditory cortex? So this is something that is lying there for almost half a century. And many people just left them behind. And I will show you something later on, and you will appreciate why you cannot drive it. And the word you have heard from talk this morning is because auditory cortex is highly nonlinear. It's the nonlinearity of the cortex that makes it difficult to drive. So that nonlinearity comes from this longer pathway from here. Okay. Now, why do I say it's a longer pathway? If you compare visual system and auditory system, and the visual system you have heard from Dr. Mangankar, sir, among others. Here's the retina. Here's a ganglion cell, output retina. And from here, you have spiking. Then you have one synapses, it's called a thalamus. Then you have visual cortex. Okay? So spike travels through one synapses, you have reached the cortex. Whereas in auditory cortex, you hear about cochlear, spike can start from here, ganglion cell. So it has to travel a minimum of 3, often 5 stages before reach the auditory cortex. So that means if you calculate the probability of having one spike here and giving one spike here, that probability is much smaller than having one spike here, giving one spike here. That's because in the nervous system, all the synapses is not strong. So that means having one spike here, the probability of having an output spike is far less than 1. Okay, it's never 1, it's always less. So when you have 3 synapses together, you can multiply it. You know, having a spike here, the probability here is very, very small. Okay, that's one of the reasons that the signal here is further processed from here than signal here and from here. Okay, driving neuron in V1 is not very hard, but driving neuron in A1 is much harder. And why we have this? Then question. So from a signal processing point of view, why we have this? We have this is because the visual signal coming here are largely in parallel. That's how the visual system processes. There's a lot of processing done within retina. Whereas the processing down here is limited only by frequency analysis, which we call tonality. And most signals from multi-sources come here on top of each other. And then auditory system perhaps needs this long pathway to gradually separate the background and foreground different speakers. Eventually, you can recognize one person out of the ocean of many other persons. So this is reflecting the very different signal processing strategy from here and here. That's from signal processing point of view. Another implication of this is that biologically, these synapses we call is highly subjective to the medicine or drugs we use in doing experiment. This is a biology side now that is engineers don't often pay attention. That is when we do neural recording from animals, in most time animals anesthetized, just like we go to hospital or do the operation, doctor give you injections of drugs, you fall into sleep. Okay, that's how many experiments were done in animal until new technology developed. In that condition, V1, primary visual cortex neuron, is still very active, but A1 is not very active. What it means for foreign. So when animal is anesthetized, and the cortex is very silent, when you play a long duration of tones, there's a little bit of response at the beginning, a little bit at the end, but nothing in between. Okay, this is very odd. Okay, and this is one of the things that delayed progress in autocortex for many years. It turns out the same animal, same anesthetic animal, if you put an electrode in V1 is much more lively. Okay, that's why a lot of visual scientists never understood why people cannot drive neuron in outer cortex. There are two reasons. One is outer cortex is much more subjective to anesthetic. Second is nonlinearity. These two together basically explain why you cannot study them. So once you have a technique that you can overcome anesthesia, then you can drive a neuron outer cortex like this. This is a study my lab published once we recorded from a weak marmoset. And you can drive neuron long and enduring, sustained. So you can drive them. But driving them is not really a story. The story is how can you drive them? You cannot drive every neuron, even animal is weak. It's just like when we are weak, our brain is not always active by every neuron. So it turns out, this is what we learned. And you can drive neuron if the signal is optimized for the neuron. Okay, so if you remember the vision, V1 talk, I hope you remember it, that in the V1, there are neurons called orientation neuron. If it's an orientation neuron, it's a selective vertical orientation. You move this way, you drive neuron maximally. If you move orthogonally, drive minimally. If you're at 45 degrees, somewhere in between. So this is called a peripheral optimized stimulus of orientation neuron. In other cortex, in A1, the peripheral stimulus has multiple dimensions. Give you an example. The neuron might need a frequency about 5.5 kilohertz. They need the sound level 40 dB, as we heard this morning, sound level selective. And they need it from a location 25 degrees to the left, 15 degrees above. They need amplitude modulation at 64 kilohertz, 64 hertz, so far so on, bandwidth, all of that engineers are familiar with. If you tune all those parameters, it's often multi-dimension, 2, 3, 4, 5 dimensions. Then you can drive neuron like this. Otherwise, you can also drive neuron transiently, even animal is weak. If you do this, you can drive neuron in primary outer cortex, in secondary outer cortex. So the message is here that you can drive neurons into sustained firing by peripheral stimulus. This peripheral stimulus is we don't know why we don't call it optimum. And since if you know mathematics, you will know in order to call some optimum, you have to exhaust all the possibilities in the entire space. When you have multi-dimensional space, as I mentioned, the frequency, intensity, all of that, the time you need to test that space is too long. When you study, this is biology, study neuron, we have somewhere between half an hour maximum to study neuron. So you have to do everything within that or you lose the neuron, okay? Because the neuron is only 30, 40 micron, that size. You drop your electrode, it's like fishing in the deep sea with a long, long hook, okay? So we call it peripheral approaching optimum stimulus. So let me explain to this. This is something that I think is very interesting and it should have a value to engineers. So if you look at the process in a computer that we design as a filter has a frequency, it's selective, you can put other parameters. Okay. A neuron, if you equivalent that to the process in a computer, then it is a processor with a multi-dimensional selectivity. Okay. What does that mean? That means if we look every neuron in the brain, if a brain has a million neurons in outer cortex, let's say I have 1,000 neurons. If I take a stimulus, any stimulus, tone, anything, I play that to every neuron, then I line up neuron by how much they prefer stimulus. Neurons that prefer the stimulus I play, let's say a tone, will respond sustained throughout the entire duration. The neurons that least prefer that just respond briefly. Okay. You take any tone, a voice, a music, a tone, anything you play to a brain, look at every neuron, you line up this way. Then you can ask questions other way around. If I look this is from a stimulus point of view, from neuron's point of view, if this neuron, this two-dimensional space is the entire acoustic base, just for the sake of illustrating two dimension, a neuron would have a peripheral stimulus here that will respond as sustained. That is, as long as stimulus sound, it will be responding. Then the blue area indicates stimulus and neuron would respond transiently, just peripherally. The white area would be the stimulus and neuron has no response, right? So this is like a neuron as a filter. The filter is highly, highly selective. Okay, this area is very small. So it's likely with David Hubel 50 years ago when he was looking for the neuron, he cannot drive this because the space is large. He was wandering around most time in the white area, occasionally touch blue. Why we can't get this after 50 years? That's because we have a computer and we're engineer. And we can have a computer synthesize stimuli in all the dimensions, and the computer controls testing. Then we can eventually reach this spot. Now, what does this mean? If one neuron has this hot spot on the acoustic space, because the brain has many neurons, if all of this hot spot accumulate, then you can represent any sound that it can present. This is very different than the computer we're making. A computer processor, none of them is as highly selective as one you will see here. This is how people call neurons in the brain are sparse. In the sparse is another term that you can call it selectivity. Okay. Now, how is this different in the cortex than subcortical stations? So if you look at the first stage, an auditory nerve, which you hear this morning, the neurons are not selective. This is almost very much like the filter that we know in the signal processing class, that as long as you put energy there, they drive this. As you move progressively through the stage, from inferior to thalamus to cortex, this red spot becomes smaller and smaller, neuron become more and more selective, or you can say more and more sparse. That's the dimension that going this way, okay? So now we can know why David Hubel cannot drive them, because auditory cortex neurons are highly nonlinear and selective. And this high selectivity reflects specialized processing beyond the tonality organization established at its Cochlear. This is the first message I would like you to know, okay? Now, the challenge for us as engineers or neuroscientists alike is that if brain transform isomorphic representation faithful to non-isomorphic representation, how do you know what to look for? Okay. If you don't know what is being transformed inside, how do you look for? This is really challenging. Second one is that now if you take it further, if you transform from acoustical to perceptual dimension, what is perceptual dimension looking for? So those are the challenges when you study the brain, when you look at neuroscience literature. So the faithful transformation is easier to understand because it resides heavily on the physical parameters, whereas the internal representation are harder to understand, but that is the message. So I'll give you one example of this transformation. What do I mean by from faithful to non-faithful transformation? This question is, how does the auditory cortex represent a time-varying signal? So why this is interesting, because if you look at speech signal like this now, speech signal like a vowel, we can present them in a spectrum. There's a frequency, amplitude. And it's periodic, so this is discrete. This is, you know, from signal processing. So this is pixel-code formats. That's a spectral representation. But you can plot it in the temporal domain. So this amplitude versus time. So you can see there are all those variations. Okay? In the signal processing term, there's a coarse structure. If we go along this my curves here, this is called envelope. Then there's a fast representation we call it carrier. This is exactly what you learn in communication. So how does the brain process this? Well, as you remember from this morning's lectures, in the auditory nerve has this thing we call face locking. There are two things here. One is in the cochlear, there's a frequency organization. We call it tone type organization. You heard this morning. You also heard this morning that each of the nerve, if you give them sinusoidal representation, it has this sinusoidal-like representation. We call it face locking. Okay, face locking. So this is a way for nervous system to capture temporal structure. Okay, but here's the trick. Here's the trick. So the neuron firing is time series, right? So every millisecond is changing. Now the signal is intended to encode auditory signal. It's also time sequence. It's 2 times the same. Okay, So you have a time series encoding another time series. How to decide the precision? You think about this. This is actually not trivial, right? If it's a vision, I have no time, I have a picture. Front of my picture, my hand, I have a one time sequence. Then back of my hand, I have another time sequence. Differentiate between the time sequence anyway can differentiate back and front of my hand. But if I give you two sounds, both of my time varying, how that time and this time go together, remember it's that same time. That's the issue here. Okay. But first of all, let's look at how well the audio system can capture this time varying signal. If it's a computer, well, you just digitize every small intervals. You capture this, right? That's what audio nerve digitizes. So if we quantify how well the first stage of audio system capture time varying signal phase locking, we plot here. 1 is perfect, 0 is nothing. It's like this. That means our audio system can capture phase locking very well until about 1 kilohertz, 1,000 hertz, and then gradually go down, eventually disappear. 1,000 hertz means 1 millisecond interval. So you can capture every millisecond pretty good. Okay. So that is the first stage. That's the limit of our system, how fast we can capture. Any change faster than this, we cannot capture. Okay. But the challenging problem is here. If you go to the next stage, over here this morning, it's called Cochlear Nuclei. You do the same experiment. That curve is here. Okay. Move towards the left. That means become slower. If you keep this going, all the way to next stage, cochlear nuclei, inferior curves, thalamus, cortex, that curve keep moving all the way here. So by the time you reach audio cortex, primary audio cortex, you repeat that experiment. You only got about, what is this, 100 hertz. That means cortical neuron cannot capture anything faster than 100 hertz. Now, if you're an engineer, I told you what does it mean. You mean we cannot hear anything on faster than 100 hertz because CDs, our sampling rate of CD, how much is that? You know that it's about 44.05 thousand hertz, right? Our hearing is 22 kilohertz. Okay, so this actually does not explain how can we hear fast varying sound in voice and in music. Okay, this makes no sense if the cortex can only capture this. Now, this actually has been shown in many experiments until 10 years ago, 10-something years ago. That is, if we play this kind of a sequence, I play a random pulse sound like click trends. This is like a Morse code, right? So it's very simple. I just play this. Okay. So then the question is, we record for neuron in audio cortex. How does it respond to this? Well, there's one type of neuron like this. There's a 50 repetition, so you can see it's line up. See, this one seems to capture all of this. All of this, not all of it. But then the other type of neuron responds like this. But if you look carefully where this neuron responded, it responded when there are a few events here. But when there's a lot of events stacked together, if you look closely, this neuron actually doesn't capture. But this neuron, when these events are sparse, that has no response. But it responds when things are piled up together. Okay. So this is a hint that the cortex, when it's processed time varying signal, it no longer uses our digitization. Because if I give this example to the engineer in signal processing classes, I say, I give you this random sequence, the Poisson distributed collect trends. How do you design a digitizer to capture everything? Well, you calculate the highest sampling rate necessary. You digitize as fine as possible in capture wall. Okay, that's how we should do. No, this is not what a brain does. So eventually, it turns out this is a response we call it synchronized that can capture certain spike events. This is non-synchronized. Here's an experiment to prove it. So we designed this sequence of stimuli that is regular, so easier for you to see. This is collection, faster, 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 right? From 10 hertz or 100 millisecond interval all the way to about 300 hertz. Okay. So the first class of neuron responds like this one. Okay. When this is slow, you see it captures everything perfectly. When this becomes faster and faster, you see start losing its eventually not responding at all. Okay. Until this paper was published, this is by my first doctoral student, Thomas Lu. This is all we know in the literature that we can capture in the cortex. It's about 30-some hertz, not even 100 hertz. This is about 30 hertz here, and then nothing. But this is puzzling because above this, if I play this to you, I actually give this as an exam for undergraduate students in John Hopkins and Beijing every year. Ask the student, you just do this exercise yourself. You use your MATLAB. Any of a student here, you can go home and try it. Just take you half an hour to do this. You write a collection platform computer, and you hear yourself. This initial ba 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 ba. Then you ask yourself, at some point, your perception would change from discrete to continuous. Okay, that point is right here. So when this type of neuron, we call it synchronized response, no longer capture click here. You actually no longer hear my individual events. But the question is still, what about the rest of them you hear? You still hear this. We think animal here. Well, it turns out half of neuron in outer cortex behave like this. When this is slow, no response. When it becomes fast enough, it becomes responding enough. But there's no time stamp. Okay. You have a pair. This is actually interesting. This is not interesting because this is reflect, even though this is easier to see. That means this neuron convert this time-changing signal to fine rate. When the increase here, fine rate increases, but no longer with the bare structure. So time structure is gone, but that time structure is converted into fine rate. Okay. So now we eventually summarize these two types of neurons. If this is how fast it is. So I say interclock interval, slow, fast. When this slow is captured by what we call temporal coding. When this gets fast enough, this type of neuron is gone. The other type of neuron becomes the response. So these two neurons together basically represent time-varying signals. So now we know in the cortex, even very fast time signals can be processed, but it's processed using a strategy different from the slow signals, using this explicit temporal coding and implicit rate coding. Okay. Now, this transformation actually does not take place at once in the cortex. Since the cortex takes from the thalamus, then we repeat that experiment in thalamus. So in cortex, those two populations is about 20 milliseconds. They change from one population to another population for temporal to rate. In thalamus, this two populations change about 5 milliseconds, about 200 hertz. Okay. So what it means that in the auditory nerve, everything is processed temporally. If you move higher and higher and higher, faster events is get processed by fine rate representation, as I'm showing here. Okay. And eventually, by the time we reach cortex, only about 30, 40 hertz is processed. Now, what's implication of this? So why some people talk about it? So in auditory system, cochlear is very fast. Like this morning you hear. Vibration here is as fast as a millisecond or even faster. Okay. And you probably know from the movies, you know how fast a visual system, right? Still probably remember. So when we watch movies, what is the frame rate of a movie? Anyone remember? Frame rate of a movie. Yeah, it's just about 25. It's just 25 hertz. 25 hertz is a discrete signal. Your visual system considers continuous. Okay, that is it. So, but our ear here, if you take the music, other things, reduce below 100 hertz is garbage, right? So our ear here, the sampling rate, if you use signal processing, ear sampling rate is about 2 orders of magnitude faster than eye, okay? And as you heard this morning from Dr. Zhou's talk, that when we watch a movie, we do auditory visual integration, because if you look somewhere at the lip, listen to a sound, if listen doesn't match, you feel uncomfortable. That means that whenever we watch people talking face to face, we always synchronize both. Now here's the problem. This is a computer, you have two processors. One processor is the camera, is slow, it's vision. One processor is a microphone, that's 2 orders faster. Then you send a signal to the CPU, you want to synchronize them. How can you synchronize them? Well, they have to operate on the same clock rate. By information theory, there's no way to speed up a slow process. Information cannot be gained there. The only way to do so is to slow down the faster signal. This is why auditory response are slowed down along the way. Through the ear, from 5 to 7 process stage, all the rich cortex, for the purpose of multisensory integration, because the visual and the tactile system are much slower. You have to slow down auditory signals so that is synchronized in the cortex. In the V1, A1, S1 clock rate is about the same. Okay, And this is also for the purpose of object processing. This is going back to Fourier transform. Whenever you do Fourier transform, you cannot do instantaneously. You have to take a window. A window has particular length. Okay, the longer the window, the more spectral information there. So when we listen to a word or music, we take each window. We never take a window. Essentially, you do this slowing down. Okay. Now, then after saying this, then I'll go back to question: how does auditory cortex represent the sound sequences? If I give a sequence, today is Tuesday. Okay. So in auditory nerve, we process this is by moment. That means auditory nerve cochlear, we sample every millisecond. But by the time we reach the cortex, we process this segment by segment. And just a long story short, in the cortex, that sound window is about A1, primary auditory cortex, is about 30, 40 milliseconds. If we move to next stage, the window becomes longer and longer. Okay, so that's information. Then for that sentence, just give you as an example, today is Tuesday. The auditory cortex neuron would mark sparse segments, just like beginning of a word, with a precise timing, and transform rapidly occurring sound into firing rate-based representation. So like today is Tuesday. Every moment that synchronous neuron capture, but today, that whole thing is computed by firing rate representation. Okay, that is how internal representation is sound. So there are a lot of details things I skipped here, but here's what a summary of a signal how. From auditory cortex A1, primary auditory cortex, the signal goes rostral, RRT, go to lateral. And the study suggests when you go lateral, temporal spectral integration window become larger and larger. When you go rostral, temporal integration window become longer and longer. Okay. So eventually, this allows us to process small object to large object in spectral temporal domain. So what is the general implication of this experiment? Non-synchronized response that I will show you are the results of temporal to rate transformation and represent the process instead of preserved information. And the synchronized information is preserved. Okay, that's not processed. The auditory cortex transforms stimulus features into internal representation that are no longer physical replica of acoustic emission. This is a very important message that I think need to be carried out. Now, the other class of signals that has of profound interest to our system is music. Okay, music. And I become interested, it's about 15 years ago, and when we began to study how the mammary brain process harmonics. And it became interesting because it turns out, if you argue evolutionarily, music is probably biologically more fundamental than speech and more universal than speech. Speech language has a lot of culture-based idiosyncrasies, whereas music carry much more universal meaning and biological meaning in this. But many neuroscientists have stayed away from here study because you don't read much of this music study in literature. It's very puzzling, right? Because you ask people, I go around and ask everyone, are you into music? I never heard anyone tell me they're not interested, either socially or scientifically. But if you look how many neuroscientists, auditory neuroscientists study music in a rigorous manner, very few. That's because until recently, I think a lot of people believe music is so human, so unique. I think it's wrong. Music is much more biologically oriented. Because it's so unique or human, if you believe so, then people don't touch this. So let me show you some example. One of the dimensions that we look into musical processing is to look at music, element of music. What is music? Music made of harmonics, rhythms, timbre, right? Melody, all of that. So if you take them piece by piece, not take them as a whole, we can perhaps learn something from animal world. So one of the things we've been looking at is harmonic processing in music. Harmonic processing in music. So when you play music, for example, from violin, you look spectrogram, it's all harmonics, right? Everything is a resonance harmonics. You can see harmonics everywhere. So, but if you look at auditory system, you have seen these slides this morning. If you look at Cochlear is a frequency analyzer, right? Cochlear acts as piano keyboard, except you only play one key at a time. Okay, Cochlear is like piano keyboard, but only one key at a time. You have frequency selectivity. And then, as you hear also this morning from Vincent, that auditory neurons along the pathway has filters like this. We call it recipient field, tuning curve, or we just call it filter. It's selected for one frequency. It's like listen to one piano key from a Cochlear. Okay. But here's the problem. Eventually, as all of you who know the music, if you play piano, you never play just one key. You play many keys together in particular pattern. So the question is, where in the brain and who is listening to piano playing? Not a Cochlear. Okay. So the question is, where in the brain this combination of keys, combination of frequency is a process. Okay. Frequency analysis is not a reason. So people have looking at the frequency tuning in audio system for a long time. Most neurons tune to one frequency. But sometimes if you use two-tone, you can have neuron tuned to several frequencies. Okay. Here's an example showing neuron tuned to one frequency. This worked in cats long ago. This is a neuron tuned to two frequencies. Okay. So as you move to a middle brain higher and higher, you see more neuron tuned to more than one frequency. So that gives you a hint. Perhaps there are neurons up there in the cortex that would be responsible for listening to multiple keys. So here is an example of neurons we recorded from audio cortex by my former student, Katia Siddhartha, who actually grew up here in India and came to the United States as a graduate student many years ago. And so here's a neuron that is actually tuned, I plot the three-dimensional way, frequency, intensity, tuned to two frequency. But the interesting is there, then you say if it's tuned to two frequencies, this neuron tuned to three frequency. So what's the relationship between this? Well, it turns out this type of neuron that tuned to more than one frequency is a minority. Only about 20% neuron tuned to two frequency in primary audio cortex of marmoset. Many neurons only tune to one frequency. So for a long time, people thought this neuron are simple. Until we did this two-tone experiment that we put one tone here, then sweep another tone. So like just always put one tone, boo, 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 boo. At the same time, we put a second tone. I systematically change the second tone, always two tone. And what you find here, this is same in this simple one-tone neuron. When we put a second tone, this place, about 1.5 times here, sudden response is much higher here. Okay. And then this is another example. The neuron was a response to one tone here. We put one tone here and put a second tone away. When the second tone was 3 times here, I actually recorded this neuron personally with Siddhartha together. And when we put it here, when we put a two-tone here, the neuron is completely silent. Okay, so you heard from Vasan this morning a nonlinearity example like this. And this is nothing like the electronic device we have. So this is a basic filter. You give a frequency, it responds, bop, bop, bop. Then you put a tone, second tone, 3 times, bop, 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 nothing. Okay, so think about the circuits, how to do it. So it turns out, if you look at the relationship between these, for neurons that has more than one peaks, the relationship between two peaks is that second peak is either twice or 1.5. And for the single peak neuron that has more than one peak, this is a relationship. That means these are the integer ratios, right? So that indicated that is a harmonically related. So we went on, did the work. This work we just published 2 years ago, to look at if there are neurons in the brain that turn to multiple 5, 7, 8 line tones. Okay, so this work was done funny. So we take tone, we play one tone. So it turns out there are a lot of neurons in the cortex. If you just one tone, it never responds. Okay, and I think Vasan has told you this morning in his thesis. He did one of very elegant work to show there are many neurons until you play two-tone in particular combination and the frequency I showed this morning. You can't drive them. But this is neuron are one tone, if super frequency, very little response. Then we put 2 tones, little bit response until play about 10 tones. Okay, we'll play 10 tones. We gradually, I think it's about 10 or 12 tones. We'll gradually change the spacing. Basically, we put a 10 tone like this. We guess the spacing. We systematically make it farther. Okay, we sweep this, and what you see here, eventually this particular combination drives neuron. This combination, this F0 is 1.05. Okay, so this neuron basically shows that it responds to a combination of all these tones. So we call this harmonic template neuron now. Okay, harmonic template neuron now, and then you can look what is the peripheral, the interval of the peripheral, the frequency are tuned to, and the interval, the peripheral, the ratio of this we plot here, they're all integer ratios. Okay, 1 integer. So if you're a musician, if you look at multiple integer ratios, your eye will light up because this suggests major interval in music. Okay. Now, to prove these neurons are truly filters that respond to multiple tones, we did this following analysis. So here's a neuron, here's one of harmonic temporal neuron that we can excite them to 200 spikes per second by about 12 tones, by 12 tones, okay? So the first one, 12 tones, is perfect harmonic. So we fix this one, we introduce jitter, okay? So once we introduce jitter, they become less and less harmonic. So it becomes less and less harmonic, eventually inharmonic. So you can see the neuron become less and less. But the problem is that when you give 12 tones, there are many dimensions. You can make them closer, far away. You can move them around. And how do you know all of them are useful? What about we deleted some of them, right? So this is a high dimensional space. So eventually we apply methods that the engineer use is system identification. So that means you have black box system. You don't know what is parameter structure. You want to learn parameter, what do you do? You put a white noise in, get output, you mathematically compute. This is called white noise analysis. Some of you might have learned this. We apply that. Eventually, we compute this neuron's transfer function is this. Okay, this is essential filter. This is frequency is weight. So this neuron has a 3 excitatory peak, 3 inhibitory peak. That means there are 3 frequency. You would excite a neuron, 3 frequency. You would inhibit a neuron. Okay, and those 6 frequency are all harmonic. So this is 3 neuron harmonic here, and 3 harmonic here. They're all harmonic. They're not random. Okay. Now, how do we prove this filter is what this neuron respond? Then after we compute the filter, we made the stimuli exactly match here. Then we switch it. Okay. So if a neural filter is like this, and make a stimulus match it, prediction you have maximum response. Then we switch them halfway, you will have minimum. We switch back again. Okay, that's what we did. That's what we show. 0 is the exact match. Then we switch coming down 1 cycle, 2 cycle. Okay, so this is what we call a combo filter in the system analysis, right? So this is one example show that the neuron like this do exist in outer cortex, and they can potentially quote listen to multiple piano keys being played at the same time. Now, this is just the tip of an iceberg for students who are interested in mathematics and engineering analysis. You can already see the way we show this is inadequate. Because when you have a 5, 7, 8, 9, 10 frequency component, the high dimension, I told you earlier, we only have about an hour to study each neuron. To exhaust that space, you need 8, 5, 10 hours. So what we show is tip of the iceberg. How would you eventually understand how many neurons there are, how many dimensions? And we are now in collaboration with Cortex with computer-driven methods to do modeling-based analysis. That is, we have 2 computers. One computer randomly generates a lot of sample space, play to neuron. Another computer record and use a gradient descent method, immediately calculate what is the next batch and drive it again. Use 2 computers because humans are not good enough now. And eventually, you can imagine you put a deep network learning into the process, use not a track neuron. Now, single neuron like this is far more complicated than some layer in the deep layer learning things you're learning now. Those are simple, very simple, really very simple, trust me. But this kind of selectivity is what allows our brain to process a lot of signals out of a background. This is what is it. And I think we have a long way to go to understand that. And of course, understanding an individual neuron like this would have a tremendous implication to build maybe future generation of a network of more selective units. Now, one would want to know that what can we learn from this kind of neurophysiology that inform on human perception, because for us doing neuroscience, and I think it's for engineers as well, for building devices, one of the goals is always how you benefit human society, for human understanding, because we study animals not just for the sake of studying animals. We want to study animals from there to gain understanding of human auditory perception. So here, I'll give you a very interesting example. Example comes from here. There's a phenomenon we use every day in speech. It's called pitch. So we have this organ here. In male, is a bump here. In female, you don't have bump, but we have this behind here. We call it vocal fold. Whenever your voice, there's a vibration. This vibration is about 100 to 200 hertz. We call it pitch. Okay, and that gives us the sense of male and female. If you're an engineer writing the computer program, I have to show you. If you ask, you say you are only allowed to use one parameter from speech to tell male and female. That's parameter use. All you need from this male and female. Okay, we use every day of this. And in language, tonal language, like my native language, like Chinese, pitch is crucial linguistic cue. So I don't see any native Chinese speaker here, so I'll give you a test. So my last name, Wang, in Mandarin Chinese, there are 4 tones. It sounds like this. Listen. Wang, 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 Wang. Okay? It's pretty confusing. I think Indian are better than Europeans, better than Caucasians, because more tonal. If I say this to Americans, native, Europeans, this is completely just at loss. So what I did is I did not change the syllable, I did not change the spectrum of my voice. What I changed is the pitch contour. So if I give you a hint, if you watch my laser pointer, show you the trajectory of my pitch, you'll get it. So it's Wang, 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 Wang. Okay. So in native Chinese, that is just like a music notes, tuned. Is every one is categorically perceived. So my last name, if you say it properly, is this one, Wang. Okay. So if you say Wang, no, it's wrong, right? So it's that sensitive, okay? So that is for native, Chinese is not alone in this. In many tonal languages, Persian, Asian languages, they all use pitch in some ways. But in English, pitch is also used. We call it paralinguistic cue. For example, when I say, are you sure? Raise my voice, I'm skeptical, right? You say, I'm sure. That's very confirmed. So pitch is one of those cues. It's probably number one, very important cues in speech. And then also pitch is very important in music. Okay. So about 15 years ago, a graduate student and I, we decided to see whether we can find a neuron in marmoset brain that encode pitch, because this is a long shot. So all the auditory people know pitch are important, but no one actually know where to find them, because we know somewhere in our brain it has to be processed. And then what we did is the following. So another thing about pitch, interesting. This is really I always use example for engineering students, because this is something you really should know, and the biologist doesn't necessarily need to know this. Is that when we listen to pitch, we also have a phenomenon. It's also a nonlinear phenomenon. It's called Miso Fundamental. That is, when I give you a pure tone, 100 hertz, you hear it, okay? Then if I play another year, a combination tones, 2, 3, 4, 500 hertz, okay? I play those 4 tones in 1 year, another year allow you to change the frequency of one tone. I say match them. You match them 100 hertz. So you hear 100 hertz out of this, but remember, there's no energy at 100 hertz. What you hear? Well, in the absence of the energy, your brain did a calculation. You compute 100 hertz out of this. This is one example of auditory computation. So this complex, because it has no energy at a fundamental, we call it Miso Fundamental. And if you move this to higher frequency, 5, 6, 7, 8, 900 hertz, you still hear on 100 hertz until you change the interval to 250, you hear 250. This phenomenon, we can hear pitch out of harmonic complex, that Miso Fundamental, was realized by Bell Lab electronic engineers more than half a century ago when they designed telephone line. Because I said earlier, the fundamental pitch here is what we tell male and female. But when you transmit the signal from a telephone line, if you transmit all the way to 100 hertz and below, it costs a lot of bandwidth. They realize that without transmitting this fundamental frequency, humans on our end can still hear pitch out of this. So anything lower than 500 hertz was never transmitted on a real land phone, nor on cell phone. Okay. So in a way, engineers make use of this biology phenomena for decades. For this, so this is something you use every day. So the question is, how does the auditory cortex, given everything you learned so far, from my talk so far, from Dr. Sadabanka's talk so far, we actually have no clue how this is. I can tell you how this is processed. But how the Miso Fundamental process, we have no clue. This compilation is similar to this example in vision. So if I show this, I say, what did you say here? Well, you say, I don't say much, but I give you a hint. You will say a dog here, right? You say a dog with head here sniffing on the path here. Well, there's no dog here. Your visual system detects dog because you carry out nonlinear computation. You connect the dots. You compute a dog out of this background. That's similar to pitch. So eventually, we identify a region, very small region, about 1 millimeter in diameter. In mammal's brain, the neuron here seems to encode pitch. There's a black square. The rest are the other neurons that you will hear a lot today. Okay. Now, what is a real pitch neuron? A pitch neuron is like this. If a non-pitch neuron will give tones at a different frequency, it would respond with tones hit its best frequency. Okay. It's tuning curve here. But if you give this harmonic complex, only first one responds because this one fall into here. The rest of them is outside this. It has no response. Okay? A pitch neuron will do this. If you play pure tone to a pitch neuron, it will respond. But when we play the combination of these tones, all of them give the same pitch, as I just said earlier. It responds as if you carry out a computation. Okay? Now here's a more example showing this. Another pitch neuron, you give a pure tone, you see it's tuned to 174. It's very low. This is about a female pitch. Male pitch is about here. Okay, it's here. But if we take this is a fundamental. Second one would be here. Third one would be here. If we give a second, third, fourth, none of them will give response until we put them together. We put the first three together, all of them shift and give a response. Okay, so in last about 10 years or so now, after this work published, there are about 5 studies in humans, and this work actually published more than 10 years now, 15 years. Okay, and there are 5 studies now in humans identify region in human brain. This is human low frequency of A1 that also encode pitch that mirror what we find in marmoset. So this is marmoset might be familiar now. Frequency high to low, low to high. Right in this corner is pitch region that mirror here. And the harmonic temporal neuron I just showed you earlier that I tuned to quote a piano keyboard playing, those that are scanned everywhere. Okay. So pitch neuron is in a very low frequency because in humans, when we hear this fundamental pitch is below 800 hertz. Okay. So what I want to show you here is that these kind of neuron, pitch neuron here, and harmonic temporal neuron scattered around suggests that perhaps the outer cortex has more neuron like this that encode not a single frequency, but a structure. Okay. In vision, this will be you have neurons that are tuned to basically curvatures, multiple patterns in outer cortex. So, and that's what I mean. But finding these neurons, in either case, extremely difficult. It's literally finding a needle in a haystack. Because in order to find a neuron, you have to search hundreds of neurons. Okay, because you have no idea where they are. So these are done with microelectrode. I just said tiny electrode put in the brain. So more recently, we've been, and so what I'm saying is here, this is just the beginning of the story. This is far from the end. It's just tip of iceberg. We don't know how many other neurons are encoding harmonic structure like this or even more complex. So more recently, our laboratory has been developing an optical recording technique now that allow us to record many neurons simultaneously. So the way you do this is by open the part of a bone here, remove the dura, that is a piece of tissue covering, and put the artificial dura that is transparent. Then inject the virus carrier calcium indicator, then we can record for neuron many at the same time. Okay. So with this, with optical device that we built and by the graduate students. So my laboratory, every graduate student is an engineer. I only take engineers or a student with a quantum background to do this kind of work. Because this is what we build. With this, then you can image it like this. I'll just give you an example. Show you a flavor of, see if I can play the song. Can this play out the song? Let me see if you can play. So to show you this new optical imaging technique, what can you do? Okay, that's the brain looking through a microscope with those blood vessels. There are many neurons down there. Okay. And what I'm going to do is I'm going to show you the activity in auditory cortex while animal is listening to a piece of music. Okay. So those are the individual neurons. This is called two-photon imaging. Then we have another imaging modality is more wide field imaging. You can see go to the areas. So I'm going to play a piece of music. Here shows the two-photon imaging. You can see the individual line up. And then here the entire cortex here. You notice there are patches. Where is that pitch region? That pitch is somewhere around here. And if you pay close attention, there are melodies, harmonic in the sound that seem to enlighten this. Okay, so let's just give flavor. So eventually what we like to understand is that when we listen to a piece of music, how does auditory cortex activate to process harmonic, melody, all of that? Okay, that's where we're going now. So, and now, by now, some of you must be wondering, you do all of this in the monkey species. Why do they care about music? They don't go to concert. They don't speak Mandarin Chinese. Why do they care about this? Okay, and it took us 10 years to train animal to differentiate pitch. So in humans, when they say ma, 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 wang, 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 all of this, Chinese, whatever, you can do this. All of humans, people have studied, we can do the very, very careful pitch discrimination. And we just published a study recently, we showed that using the most rigorous human psychophysical criteria, I've showed here, marmoset satisfy each of all of them. So even though they don't speak Chinese, they actually can discriminate harmonic pitch very similar the way we do. But why they do this? Perhaps because they listen to others. Okay, listen to others. That's a story that we'll continue to understand. So it makes sense now that they have a region in the brain that processes pitch because they do listen to pitch. Now, a broad issue for this pitch harmonic is the following. So as you have heard by now, you must recognize this picture from some of the previous talks. In V1, there's an organization beyond the position of the eye. We call it ocular dominance or orientation, right? That's the organization. But in auditory cortex, the only thing we have told you through 3 lectures today, the only organization in auditory cortex is the frequency. But frequency organization is established in the ear, you heard this morning. It's not in cortex. So what would be equivalent in auditory cortex to orientation tuning? So one of the hypotheses we have now, we're pursuing, is perhaps it's a harmonic organization, that how the neurons are organized harmonically, that is equivalent to orientation in vision. But why should we expect harmonicity to be an organization principle in auditory system? That's because harmonic sound are everywhere in our hearing environment. They are produced by vocal apparatus of human, animals, and by music instrument, and also as a result of nonlinear characteristics of acoustic generator reflectors. The cochlear also generates this. So essentially, harmonics are everywhere for us, for our ancestors. Given this widespread existence of harmonicities in our hearing environment and the data of our ancestors, it is reasonable to expect that it be reflected in the evolution and the development of harmonics. Now, the work I've told you so far was done in marmoset. This is one species of New World monkeys. And many animals around here are Old World monkeys. Actually, recently, there's an interesting and a little bit controversial study just published by a group from MIT. And they use imaging techniques to look at the humans and the old macaque monkeys, and they concluded humans, but not macaques, show regions with a strong preference for harmonic sound. This is very interesting and puzzling. Okay, why is this? So if you look at evolution, here's where we are. It's about 30 million years ago, American continent drifted away from Europe and Asian continent. And then there, monkeys continue to evolve. We call it New World monkeys. Marmoset is one of them. And about 5 million years later, Old World monkeys deviated from human lineage, come here. So all the monkeys you're seeing here, among other places in Asia, called old monkeys. So now there's a region in the human brain that processes pitch. There's a region in marmoset brain that processes pitch. If the study that just published is true, that there's no pitch processing here, then you can either argue this pitch region, if they're right, then you probably have argued that the pitch region are evolved after this and in parallel through here. Or if they're wrong, if these monkeys do have a pitch processing capacity, then maybe pitch region, its precursor, exists long before this. Why is that important? Because to music, because the music is actually very recent to us. If you look at the oldest instrument of music that on Earth, it's 42,000 years ago. In the course of brain evolution, this is nothing. Okay. So these things suggest perhaps our capacity to listen to music and the preference to a certain music structure resides in our brain structure long before musicians can compose music, or long before we have ability to make a music instrument. This is our brain that drives our hand to make an instrument that produces sound that pleases our brain. Eventually, we materialize that, become a writing composition. Okay, that doesn't mean for this. And so why do we listen to music? I want to finish this by showing you more recent work I've been doing in Beijing in collaborating with neurosurgeons working on human patient, because after all, humans do listen to music in a way different than animals, even the monkeys. So what we did is the following. When it's come to music, why we do some music? One reason to argue is that music regulates our emotion. So the reason we listen to music is not because arts. It's not because all the fancy reasons modern people gave them. It's because of basic biology. Okay, every year I talk to students when I give lectures. I ask students questions. I'm going to ask you one more time. Here's a hypothetical questions. If you are allowed to have money, wealth, anything you want on Earth from here, for the rest of your life, anything you want with one condition. That is from now on, for the rest of your life, you are not allowed to listen to music. Would you take the offer? Raise your hand. Would you take the offer? Well, some of them, but very few. But most people are stunned. But you think about this question. Okay, when I say, what do we need as a human being to survive as a species? We need air, we need water, we need food. Well, we need to make babies, right? Without this, well, we're not going to survive as a species. But without music, you're alive and well. You can eat, you can drink, you can marry, all of that. But why you need music? Why is it so hard for you to give up? I ask a question anywhere. I mean, there are a few times, but by and large, people shocked. You think of why? One reason could be music is so essential to our soul, however you define that we need that to modulate our emotion. We need that. We need that comfort us, right? So it's the emotion component. But whether that emotion component exists in animals, in monkeys, is not clear, but definitely in humans. That's one. The second about music, what is amazing about music is memory. Memory that we haven't touched upon here at all. That is, if anyone here knows music, you can learn music and remember a piece long time after you can play them exactly the way it should sound. Okay, so there are two studies I've been doing to fulfill this curiosity in Beijing. One of them is music. We want to know where in the brain, when somebody record music without any sound, what is it like, right? So let me go back here. So here's the experiment we did. So we found the human volunteers who are patients who are undergo neurological surgery. So surgeons implant electrodes in their brain. Okay, and then we can record. Then basically what we do is we pick up 10 pieces of music that are familiar. Ask them to rank this. How familiar? The top 3 that are so familiar, like Happy Birthday to You, right? You can sing it in your head. Okay. Then we just say, listen. So we play them a little bit. Then ask them to record. We play Happy Birthday. They finish the rest in your head. Then we record the entire process. Okay. Then we did a control experiment. So here's what happened. So when they listen to music, we play music to them and just listen to the whole thing. Okay. Here's light up. You all know where it is now. This is auditory cortex, including pitch region. When they record music, it's here. From the cortex, premotor in there. This is our record music. Okay. And what's interesting is that we analyze dynamics. When they listen to music, we find activity starts from here first, and it goes from auditory cortex to frontal cortex. When they record music from here to here. This work just published about 2 months ago, if you're interested. Furthermore, we look at dynamics of, this is the ECOG signals. When they listen to music, so music signal is plotted here in black. The neural signal is blue. So activity here dynamically track this. This is not surprising, given everything we know. But when they record music, the neural response more or less tracked. It's more sluggish, but still track it. Okay. So this is the beginning of the work that eventually perhaps we can show exactly how the brain when we record music. Because this is very interesting as an engineer. You think about it. I give you a long piece of time signal as a recording, or you record a tape. But brain doesn't run a tape, right? How do you record a dynamic signal with time in the brain that doesn't have a rotation mechanism? And then later on, you play back at the dynamic signal exactly time precision. This is very intriguing. This is one of the big problems, okay? How about emotion? So I've told you about this earlier, and we don't know any of this has anything to do with emotion. So, but if you signal leave auditory cortex, it goes to structure right below is here, okay? It's called insular. So insular is below our cortex. This is not in this pathway that we've discussed so far whole day today. Signal goes here from the cortex for memory, other things I just talked about. But it also go deep into this place called insular, deep here. Okay. So we had a chance then to analyze insular. We recorded for a number of patients. We analyze insular from different regions. Eventually we'll show you this. Then we play the patients, the voice that has different emotional contents. Some of them amneutral, some of them scary, some are happy. And then we show that part of insular, anterior insular, and amygdala, that's another structure, show the preference to emotional signals. Okay, show emotional signal. Whereas the auditory cortex, gyrus, and the posterior insular doesn't. Okay. Now, people knows amygdala has response to emotion for a long time. The division of insular to emotion is more recently discovered. And then we drop the since the physician has the electrode in the insular while doing experiment, they were excited, you can stimulate it with a little bit current. So it turns out if you stimulate this part of insular, patients will report emotion as well. Okay. So anyway, so that's the study that's eventually. So in the last couple of minutes, I'll just very fast run through another line of work that some of you might find interesting. That's considering speaking. One of the things so far is about just listen. And this is important. I won't have much time to expand, but I just want to shed some lights on this. That if we take one step back to our auditory system, here's the auditory system operates in 3 pathways. One of them is what we call ascending pathways for the coding that you have heard from Dr. Zhou, Dr. Sargampa this morning, and my talk until now. That from ear to brainstem, cortex, frontal cortex. This is what we process sound. Another pathway is called vocal control, that we control what I want to talk, as I'm doing now. But we don't do these things separately, right? We listen, of course, we talk. But when we talk and listen at the same time. So there's a third pathway that's completely ignored by literature, but not by literature, by the textbook. You don't read this. Is that when I talk, as I'm doing now, the sound comes to my ear right away. There's a feedback, okay, as I'm doing now right now. This is turned out to be a very crucial pathway. So why this is interesting, that's because when we do speech, it turns out if this pathway is interrupted, we cannot learn language. We got stuttering, all of the problem. But how do you study in animal models? Okay. The model until now is really some birds. But now we have a marmoset as a model to this. Now, I think by the time finished today, all of them should know marmoset, even though you had never seen a real marmoset. Come to Baltimore or Beijing, we'll show you a real marmoset. But why marmoset is interesting? Because it's a thing, it's talk. Okay. Now, where is marmoset? This is all the monkeys in the world. Marmoset come from here. Okay. And all the monkeys, the audience are familiar is here. Okay. And they're interested here. This is where they live. Okay. They live on the trees, and there's a real marmoset here. There might be another dozen or so around. Okay. They can't see each other well, so they talk. So, and not only they talk, they have all other interesting, if you're a biologist, here's probably why we choose marmoset. Okay. I began to work on marmoset when I was a postdoc in middle 90s. Then when I started my lab in John Hopkins in 1995, I devoted fully entire life into marmoset work. One of the important reasons is that this monkey is highly vocal and social in captivity. This is very important because the monkeys you see here outside is very social, very nice. But the monkey people put in laboratories, they don't talk because they're inhabited. But marmoset is the exception, they're highly social. And what's interesting that this monkey breed very fast. They give birth twice a year, every time give in twins, and they reach sexual maturity in 18 months. And then you can study development. Based a year and a half, they're full grown. Okay, 18 months is 18 years in humans. It's not that fast. Okay, and what got most people interested is about 10 years ago, research in Japan made genetic manipulation. Now you can make a transgenic marmoset now. Okay, so there are many reasons that make marmoset a very attractive model now. This is one of the hottest non-human primate model in neuroscience in United States, in Japan, and in other parts of the world now. This is one. Okay, and because it's only small, only 400 grams. So experimentally, when you do biology, when you choose a model in biology, the smaller is better, not the bigger one. It's bigger, it's harder to work with. Smaller, faster is better. Okay. Now, this is the reason we choose marmoset. But marmoset also, with everything I told you so far, very nice. Their hearing range is overlap with humans. This is what we hear as humans. Marmoset basically hear all we hear. Okay. So going back to the question I asked earlier, why they care about the have a pitch region in their brain? Because actually they hear the pitch region, perhaps from a natural environment. Here's the vocalizations they made. You've seen some of them from Vincent talk this morning. A huge variety of vocalization you can sample in a colony. And the vocalization evolve from birth gradually into adulthood. And we can study this problem in marmoset. For speech, we use the vocalization. For music, we study pitch harmonicity. For deafness, we have a cochlear implant model in marmoset. I don't have time to talk about it at all. And a lot of people are interested in marmoset now because they're highly social animals, very friendly. So you can use them as models to study autism. Okay. And we've been using marmoset basically in two ways. One of them is as a general model to start hearing, which I talked about you today. Another one is using the model as a neuroethology, so speaking, which I will show you very quickly. That's because audio cortex is here. What control our talking is Broca area. Okay, this is listening, and people have shown for a long time in humans. And if you electrically stimulate this part of the cortex, you generate speech interference. Okay, but we really don't know the circuits because in humans this is a very rough diagram. We have no idea how it's working, and then more and more evidence indicated that is an area responsible for production influence audio cortex. Okay. So one of the questions this is a question that students also find fun. I think my last experiment I'll tell you, I'll leave you with this question. You probably remember, if you don't remember anything else. Have you ever heard particularly for students who have learned foreign language also, have you ever heard your voice recorded tape recorder and play back to you? Yeah? How do you feel? Does that sound to you? No. I asked a question anywhere I go. It's a universal answer. We listen to our voice, record tape recorder, and play back. It does not sound to myself, right? Why? Why is that? Or you go to Google's, you type in the same question, it tells you it's a bone conduction. Everyone tells it's a bone conduction, right? Because when we talk, we have a sound come here in the air conduction, our bone vibrate. When we play back for tape recorder, you only have air. But bone conduction is a low pass filter, you can counter that. After you take into account that, it still doesn't sound like yourself. Why? Okay, here's the reason why. Because your brain fundamentally alters the signal you talk to yourself. So this is a very interesting scientific phenomenon. Eventually, we'll be writing into a textbook, you see explanation. That is, our voices, only we know our voice, what we think it sounded like. Everyone else in the whole universe listens to different. It's like emperor has no clothes, right? Only emperor doesn't know. Okay. Why is this sound different? That's because there's a mechanism called audio-vocal interaction. Okay. So here's something, a little quiz I give you. This is a copy from a popular textbook some of you might use in your class. Okay. So this imaging experiment to show this, in this case, someone look at a table, okay, then the brain light up. Where is this? Visual cortex, okay? And someone listen to the word table. Where's the light up? Auditory cortex. All makes sense. Okay. Now look at this one. Okay. Someone speaking of the word table, light up here, motor, right? This is motor cortex, the apple. But when someone's speaking the word table, does her hear the word table? Yes. When you say table, you hear yourself. But why auditory cortex has no signal? Okay, that's what puzzling. When you listen to the word table, your auditory cortex light up. When you speak in table, you listen to yourself at the same time. There is no signal. The textbook has no explanation because Arthur doesn't know. This actually is abnormal. Okay? So question is why you're missing. It turns out, actually, there are a lot of studies, people have done this, like this one. This is a neurosurgery study. They put an electrode on your brain when you record. They play the word, let's say, today to you. Then ask the patient to immediately repeat the word. So you listen to the word, then you repeat the word. So when you listen, you have this much signal. When you speak, you have much less. So in human, this has been shown. And we accidentally found this in marmoset almost 20-some years ago. Okay? So we record from marmoset auditory cortex. You know, everything I told you so far apply, everything until this monkey vocalized. Everything I told you is true until now. Then suddenly monkey vocalized. Ooh, you see, specs is gone. It's very puzzling because the monkey vocalized is very loud. The sound comes to ear. Everything I told you, if you pass the exam until the point, you see this is wrong because everything I told you so far, Dr. Salakampa told you so far, apply, it should say they should have a response, except it doesn't. Okay. And as it turns out, we averaged many of the trials. The response disappeared 240 milliseconds before actual animal vocalized it. Okay, let's finish. Okay. So why the speaking and vocalizing suppresses? And then people have done this experiment, and that in humans, if you stick your ear, if you take the voice you say ah, you feed it back, you artificially make it higher, you hear ah, what you gonna do? Well, this is a classic feedback connection, right? You will say ah, right? And that turns out, what we found there is a potential mechanism for this what we call a feedback connection. So we did a following experiment. So we put an earphone and a marmoset. So when marmoset vocalize, we shift up the frequency. Okay. When we shift the frequency, inhibition is gone, the neuron become excited. Okay. So because I'm running out of time here, so let me just give you a summary. So the average, with normal vocalization, the inhibited frequency shift is here. So here's the summary. When we hear sound, so here's the ear, middle brain, auditory cortex, then it goes somewhere, is a motor pathway. Okay. So when we hear sound from externally, it's just coming here into auditory cortex. Okay. Everything we told you so far apply, except when we talk. When we talk, apparently, somewhere in the motor system, send the modulation to auditory cortex suppresses. But it's not just suppressing, it's modulation. Now, why we have this pathway? So when you talk yourself, when you learn from your language, you must listen to yourself and decide whether what you said is what you want to learn. For example, you learn from language first. You have to compare. If you cannot compare, you can't learn. If that arrow is greater than 0, you continue to do it until every signal is here. So we believe this modulation is part of this system. So in summary, so when we live in a natural environment without resistance, and here's the questions that we eventually want to know. we want to know where the sound comes from. Dr. Zhou told you some of this morning. And what does it mean? And very importantly, who is talking? Is you're talking or somebody is talking? Okay. And this likely involves the processing in STG and from the cortex, which we talk about, not talk about. And let me going back to David Hubel. And before he passed away a couple of years ago, before he passed away, in 2012, he had an interview with Neuron magazine. And the reporter asked him, Dr. Hubel, what would you do if you live one more time? He said, my first choice, if starting anew, would be to explore the cortical processing of auditory information. There must be secrets on Earth in exploring the neuron base of our perception, language, music, and voice. So I hope some of you will find auditory system interesting and perhaps study it down in the future. And can I take 2 more minutes? Okay, so that's my talk, but in next 2-3 minutes, I want to share with you something that I've been doing lately. I thought it was very exciting. I think some of your students may find it interesting. So in the last 2 years, I've been leading a new institute in Tsinghua University in Beijing. I was asked directly. Tsinghua University is China's IIT, so to speak, or Americans' MIT. And it's a huge engineering university. So we established a new research institute we called Tsinghua Laboratory of Brain and the Intelligence, THBI. And to address questions that very much fit this workshop exactly. So we want to ask a very important scientific question, biological question. That is, what is the biological basis of intelligence or cognition? Because all you know that artificial intelligence is becoming really hot and interesting. But artificial intelligence, as we know now, is not really intelligence. We also want to know, by doing so, how to build human-like artificial intelligence system. Now, I'll put 2 errors here, is that I truly believe that understanding brain helps improve artificial intelligence system. But as engineers, I also believe that using AI technology can help us, help biologists better understand the brain. It's go both ways, okay? And for doing so, we are building a facility in Beijing with the Marvelous Research Center doing the kind of work we talk about with a neural imaging facility and on the site. So the idea is the following, let me summarize this. We like to study the human brain and the monkey brain and the AI brain together under one roof to eventually gain a better understanding of the human brain and its applications. So the scientists we're hiring are from those disciplines. So we institute is a standalone independent. We have its own building and facility, and we're recruiting student, faculty, and globally with 3 disciplines. One of them is artificial intelligence scientists, computer scientists, electrical engineers, physicists, and system computer neuron scientists, and cognitive scientists. All of them working in one roof in an environment that conducts research entirely in English environment. And we're recruiting faculties, post and graduate students. So if you know anyone who are interested, write to email